Imagine you're out on the open water, riding in a sailboat, gliding across the ocean. No engine, just the wind. An incredible form of propulsion that has powered human exploration for thousands of years. As a child, my family and I periodically went sailing. I'd like to tell you that my earliest memories of sailing were happy, but honestly, I mostly remember the motion sickness. See, sailing was my father's passion, not mine. But one day, I was struck by not the beauty of sailing, but the beauty of the sailboat. In many ways, sailboats look quite simple, yet in fact, they are brilliant demonstrations of engineering. The culmination of thousands of years of research and development. And for what they lack in speed, they make up for with efficiency. Today, I'm going to tell you about my work with another form of propulsion that I believe will power human exploration well into the future: in-space electric propulsion. Now, many of you are probably not familiar with spacecraft electric propulsion, but some of you probably own an electric car. And like you, I first learned about electric vehicles through cars, not spacecraft. In college, a good friend of mine and I co-founded the University of Illinois' Formula Electric team. These are 600-pound, student-built, open-wheeled race cars capable of going from 0 to 60 in as little as 3 seconds. Not only was it fun, but it provided me with many of the experiences and insights that continue to influence the engineering that I do today. Electric vehicles convert the chemical energy stored in batteries into electricity, then that electricity into motion. For cars, using an electric motor. Electrically propelled vehicles are everywhere. You'll see them as golf carts, buses, e-bikes, riding lawnmowers. The other day, I was taking a walk and even noticed my local delivery truck is now electric. And whether or not you've noticed, most spacecraft in orbit today are electrically propelled. So how does propulsion work in outer space? While some have tried, electric cars don't work in outer space. In space, you need a reaction mass, something to throw in one direction to propel you in the other. Rockets, like those that carried humans to the moon, and spacecraft beyond the edge of the solar system, use combustible propellants as reaction mass. They burn fuel and oxygen, which creates pressure, and that pressure expels gas, which propels the rocket forward. Now, our society holds rocket scientists in the highest regard, yet rockets, like the combustion engine, do have limitations. They consume significant amounts of propellant. And the last time I checked, there's still no gas stations in outer space. So, the further we travel away from our planet, the more efficiency matters. Because as soon as a spacecraft's gas tank runs empty, its mission is almost always over. By comparison, in-space electric propulsion sips on small amounts of breathable gases as propellant. Not enough to lift anything off the surface of the Earth, but just enough to move a spacecraft that's already in orbit. Furthermore, we collect the sun's energy on solar panels, and then we convert that to electricity. Combining that electricity with gas, we create plasma, a super hot electrically charged gas, something that I've been working with for nearly 30 years. Now, electric propulsion accelerates this plasma to amazing speeds to create thrust. And it is this high speed of the plasma that makes it important to NASA's future exploration of the solar system. Now, this isn't a very easy concept, but I'm going to put it as simply as I can. The laws of physics prevent chemical rockets from accelerating their propellant any faster than about 9,000 miles per hour. Yes, that's fast. But electric propulsion can accelerate its propellant to 10 times that speed or more. The motion of a spacecraft is determined by both the speed and the mass of its propellant. So, the higher the propellant speed, the less mass of propellant required. The less mass of propellant we need to put in the spacecraft, the smaller the spacecraft. The smaller the spacecraft, the smaller the launch vehicle. And then the smaller the launch vehicle, the cheaper the mission. So, a mission that, say, required a spacecraft the size of an SUV could now shrink to the size of maybe a household refrigerator, thanks to electric propulsion. And the last time I checked, it was cheaper to launch a refrigerator into space than an SUV. So once a rocket delivers a spacecraft into orbit, electric propulsion, very much like a sailboat, is a very efficient means of transport. For nearly 70 years, electric propulsion development has been rooted right here at NASA's Glenn Research Center. In 1964, we launched the first gridded ion thruster, and then recently developed NEXT, gridded ion system, which can operate continuously for years and was recently demonstrated on DART, NASA's first mission to demonstrate asteroid deflection. We also recently developed the 12-kilowatt magnetically shielded Hall thruster. This is the highest power electric propulsion in commercial production today and will soon be implemented in NASA's Power and Propulsion Element. But our impact in propulsion is not limited just to propulsion for deep space, but also propulsion for commercial space. Over the last 2 decades, there has been an exponential rise in the number of spacecraft operating in low Earth orbit, especially small spacecraft. In 2014, we seized on this market trend to help us finally transition our advanced electric propulsion technologies from our science labs and once-in-a-decade NASA missions into regular commercial use. Now, just to be clear, electric propulsion has flown commercially since the 1970s, but it's remained a niche technology. Chemical propulsion has been the go-to choice. However, the ambitious missions that NASA now envisions for small spacecraft demands a paradigm shift, a fundamental rethinking of how we build and fly spacecraft, especially propulsion. After decades of NASA investments in electric propulsion technologies, our small spacecraft electric propulsion project now transfers a wealth of knowledge to industry. We've done this by miniaturizing our advanced 12-kilowatt technologies into a small 1-kilowatt package. In other words, it contains the full DNA of NASA's electric propulsion heritage, but with much less risk of back injury. Our project's goal is to lower the bar to infuse advanced electric propulsion technologies into industry, both commercial and NASA alike. Our 1-kilowatt thruster is not only well-sized for transferring this technology to industry, but it provides a performance boost over classical Hall thrusters. In the past, just 1 decade ago, a Hall thruster could operate for maybe 3,000 hours at this power scale. Today, we have demonstrated with our design 11,000 hours of operation on one thruster. This test was conducted on Northrop Grumman's NGHT-1X Hall thruster. It's a version of NASA's 1-kilowatt design that they've licensed and now commercially produce. This success story is proof that NASA's investments in innovation paired with smart commercialization strategies work. And through collaborative agreements, we can not only support our licensees with the early demonstrations of modeling, but we can also help them all the way through qualification testing. Soon, Northrop Grumman will launch 3 satellites into Earth orbit on a groundbreaking mission. These satellites are called mission extension pods. Right now, in geostationary Earth orbit, there are numerous satellites running low on propellant. Each of these mission extension pods will be able to fly up to GEO and to provide up to 6 years of life extension. What would have become space junk now continues to have purpose. In full, we have over a dozen licensees of the small spacecraft technology suite, which includes the patents and know-how needed to produce a comparable system. Furthermore, some of our licensees produce complete propulsion systems, but many produce subsystems, components, or even just materials. We see our greatest impact is supporting and encouraging a thriving ecosystem for electric propulsion in the United States. We have eased adoption through open licensing, and then we support our licensees throughout the technology development process. This approach helps ensure that NASA can one day buy back these advanced systems from a thriving domestic supply chain. And that supply chain will have the DNA required to build the larger, higher power systems that NASA's future missions will demand. By aligning our long-term exploration goals with the near-term needs of commercial space, we unlock a powerful win-win. We reduce risk, accelerate innovation, and ensure US companies remain global leaders in the rapidly growing space economy. So let's keep propelling forward, investing in shared infrastructure, transferring high-value technologies, inviting bold ideas, and creating a movement that will fuel the next era of American leadership in space. Thank you.